In this video, I want to talk about band engineering, which is needed for making these multi-junction solar cells, where I grow these different materials with different band gaps on top of each other. And then I'll talk about the condition of lattice matching, which is required when these different materials are grown on top of each other. And we'll see that how this requirement of lattice matching, it ties my hand, it restricts me in the amount of band engineering I can do. So let me, start with the example of three-junction multi-junction cells. And these three-junction multi-junction cells are, one of the highest efficiency cells that you can buy in market. Currently, they achieve efficiencies of around 43 to 44% under a concentration of 500 or 1000 suns. And this efficiency has been, the efficiency of these multi-junction cells has been, it has been continuously rising in the recent years. So if I talk about three-junction cell, I need to find out essentially three different materials. Let's say this is my material 1, which has the highest band gap, so it will absorb my high energy photons or my blue photons. So this is my material which is at the very top facing the sunlight. And then I'll have a material which would be below this, which will form my second junction, and this would absorb the intermediate photons, or these green photons. And below this I'll have the third junction, which would be made up of another material, and this would absorb my the lowest energy photons, which are not absorbed by these top two junctions. So let me say it will absorb these red photons. Now I can do a simple calculation. I can calculate how much of the spectrum would be absorbed by this blue energy material, and I can calculate its short circuit current. Similarly, I can calculate the short circuit current for these green and these red band gap material, and the condition is that these three have to be equal, and I can apply that boundary condition, and I can calculate the optimum band gap. So the optimum band gap of this blue material, this green material, and this red material, which would give me the highest efficiencies. So in an ideal world, if I do that calculation taking the spectrum of the sun, what I get is this contour plots, and it is plotted as a function of a band gap of this material at the top, which has the highest band gap, and then this material in the middle, which has the intermediate band gap, and this material at the bottom, which has the lowest band gap. So if I do that, then I'm happy to note that I can achieve efficiencies of greater than 50%. So I can achieve efficiencies of more than 50% using this three-junction cell. And I've made this assumption that I can extract each of these absorbed photon into electron hole pair. So I've ignored recombination mechanisms in this analysis. And then further, what I can do is I can extrapolate this contour into the band gap of these individual materials. So if I do that, then what I see is that the optimal band gap of the top material should be close to this 1.8 electron volt. The band gap of this middle material should be in between. So if I take this contour and then extrapolate it to this middle band gap material, it is suggesting that the band gap of this middle material should be between 1.3 to 1.4 electron volt. And similarly, this band gap of the lowest band gap material, this bottom material, if I project it over here, it is suggesting that this band gap of this bottom material should be close to 0.9 electron volt. So if I do in fact engineer these different materials such that I choose the optimum band gap, then I can get efficiencies which are very high. So now my job now is to figure out what combinations of semiconductors which are provided to me by Mother Nature can provide me these different band gaps. At the same time, they can be grown on top of each other. So the next chart which I'll stare at for quite some time is essentially this chart which plots the band gap of different semiconductor materials, different 3-5 semiconductor materials, as a function of their lattice constant. So as a function of their lattice constant. And the first thing I'm inclined to look at, the first material I'm inclined to look at is silicon, because it's the most abundant semiconductor, and I make a lot of chips using it. So I focus my attention on silicon. And then I look for other materials which have the same lattice constant as silicon. So actually then when I move my eyes up and down this curve to look for other materials which have the same band gap, which have the same lattice constant as silicon, then I'm disappointed, because there are not that many 3-5 materials which have the same lattice constant as silicon. The only the lone star over here is gallium phosphide, which has a lattice constant similar to silicon. So it's very hard to find 3 materials with different band gaps which can give me this optimum material set for 3-junction solar cell based on silicon. And also this band gap of gallium phosphide is larger than what I need for optimum. So it has a band gap of approximately 2.2 electron volt, which is greater than what I need for my optimal material set. So I'm hugely disappointed with the silicon. The other material I turn my attention to next is this close cousin of silicon, which sits on the right hand side in terms of the lattice constant, which is germanium. So I look at germanium, and again I look for other materials which have the same lattice constant as germanium. So I look up and down this line, and my eyes pop up because I see gallium arsenide, which has this band gap of approximately 1.4, which is one of the band gaps that I need. And then I can further see there are other 3-5 materials which have a lattice constant smaller than gallium arsenide. Some of them have lattice constant larger than gallium, and I can essentially mix these in mix these two semiconductor 3-5 semiconductor, and I can form, let's say, indium gallium phosphide with approximately equal mix of gallium phosphide and indium phosphide, and that has a lattice constant which is matched to gallium arsenide, which is matched to germanium. So, and it gives me a band gap which is close to what I need, close to 1.8 electron volt. So this forms a very good system for making this 3-junction cell, with the indium gallium phosphide having a band gap of 1.8, which is close to the optimum value. The gallium arsenide, which forms the intermediate cell and has a band gap of 1.4, and germanium, which forms my bottom cell and has a band gap of 0.7 eV. So note that this band gap is lower than what I needed. For an optimal cell, I wanted a band gap of 0.9 eV, but I'll take what Mother Nature gives me, and I'll form a 3-junction cell out of that. So this material system, this germanium, gallium arsenide, and indium gallium phosphide material system is one of the most commonly used 3-junction solar cells. And if you do end up making a 3-junction solar cell out of it, you can see over here, so I have my indium gallium phosphide. It's absorbing my high energy photons, or my blue photons over here. Then I have my gallium arsenide, or in this case gallium arsenide with a very small percentage of indium, and it's absorbing my green light. And then I have my germanium, which has a band gap of 0.7 eV, and it's absorbing the rest of this spectrum. So I immediately see the problem of choosing this germanium, which had a lower band gap as compared to the optimum. So as a result of that, since it has a lower band gap, it is absorbing much more number of photons as compared to this top and this intermediate cell. As a result of that, the short circuit current of this bottom cell, which is made of germanium, is 25, and the short circuit current of this top cell, is 14 and this middle cell is 14. So since this germanium has lower band gap, it gives you this higher short circuit current, but that's not of great use because my cell is going to be limited by the overall short circuit current is going to be limited by these top cells. At the same time, since it has a lower band gap, it also gives me a lower open circuit voltage, because open circuit voltage is directly proportional to the band gap of the material from which I'm forming the junction. So it gives me an open circuit voltage of only 0.25 at 1 sun. And germanium also has other loss mechanisms associated with it. So this germanium, since its band gap is lower, it gives me higher current, which I cannot really use, and it gives me low open circuit voltage, which limits the overall open circuit voltage of my cell. In the next video, we'll see some of the ways we can get around this problem.